All right, so I hope you're not getting too tired of hearing me talk, because here I am again, and I'm going to be discussing alchemical free energy calculations in OpenMM. And don't worry, it's not really alchemy. The results that we're going to get in the end are quite physical, even though they proceed through unphysical intermediates. Okay. Now this isn't really my work. I'm really I've adopted a number of slides from John Codera, who's been doing a lot of work in the field of free energy calculations, and also Morgan Lorenz, who's my lab mate in the Pandey group. She also does a lot of protein ligand free energy binding calculations. I'm going to introduce free energy calculations. There are many applications of these calculations and many methods. And after that, there are really two main components to computing a free energy. The first part is running the simulations, and the second part is analyzing the data. So that's how I've broken up the presentation. The third part is an exercise that we're not going to do like right here, but it's going to be in one of the breakout groups, and you're actually going to compute a solvation-free energy in OpenMM, which I think is pretty cool. So here we go. Free energy differences are central to many questions in biological and pharmaceutical chemistry. Here are some examples of some pretty important free energy differences, like for instance, what's the free energy difference when a small molecule goes from a hydrophobic substance into a hydrophilic substance? Or how tightly does a protein bind a ligand? How much more tightly does protein A bind a ligand compared to protein B? Or what happens if you do a mutation to a protein, and how does it affect the free energy of binding? These are all pretty relevant and interesting things. How do you calculate, say, a binding free energy of a ligand to a protein? One way to do this is to actually run a really, really long simulation and observe the probability of the ligand being bound to the probability of the ligand being unbound. But because it takes a long time for the ligand to bind to the protein and to come back out, if you wanted to actually simulate a physically relevant time scale of like an hour, like if you want to do an hour of simulation time, it would take you about 1 billion years to run this simulation. So it's not really practical to just run a regular simulation in order to compute a free energy. You need special types of simulations. So there are several ways. So I think the methods for free energy calculations can fall into two main categories. The first category is the potential and mean force types of methods, and the second type is the alchemical methods, which is the focus of this presentation. The potential of mean force methods allow you to track the free energy along a specified reaction coordinate. So for example, if you have a ligand that is binding to a protein, you can use, in the umbrella sampling method, you can apply an external potential to restrain the position of the ligand with respect to the protein and slowly pull it in. So if you have this restraining potential, then you don't need to wait for 1 billion years for the ligand to bind to the protein, right? You can actually make it happen with these restraining potentials. And then there's equations that allow you to get the actual free energy back out. There's also alchemical methods, and in this case, the difference between the alchemical method and the potential of mean force method is that in the second method, you just make the ligand disappear. In your simulation, you make the ligand continuously disappear, so that you're going to have some simulations where the ligand is like half there, and some other simulations where it's only like 25% there. And that's why it's called alchemical, because you're simulating these unphysical intermediates in order to get the free energy difference between two physical endpoints. The accuracy of free energy calculations depends on the complexity of the problem. This slide is really packed with information. So sorry if it's kind of overwhelming, but basically from left to right, we're going from easy problems to hard problems. And on the left, you have hydration-free energies of small neutral molecules. That's what we're going to do in the exercise this afternoon. Now, the harder problems, well, those are the ones that you might be interested in, but hopefully we'll make some progress in the easy calculations. For instance, it's more difficult to calculate a binding free energy than a solvation free energy because you have sampling problems. You need to actually move the ligand into the binding pocket of the protein. If you have ligands that are polar or ligands that are able to rearrange or change their conformation inside the binding pocket, that also makes the calculation more difficult. And if you have a really big protein and the protein can adopt multiple conformations and the ligands are really big and you're not sure what the protonation state is, then you suddenly have a ton of uncertainty in your calculation. So generally, the more complex your problem is, the bigger the uncertainty or the error in your simulations are going to be, but that's something we kind of knew already. So part one, let's talk about how we run these simulations. So alchemical free energy simulations work because of these magical, unphysical intermediates that connect the initial state, which might be your ligand in the water, to the final state, which might be the ligand inside the protein. In this series of calculations, I think there's in this one there's 53 of them, but you might, you'll be running essentially a chain of calculations. In the first step, the Coulomb interactions between the ligand and the solvent are gradually turned off. In the next step, the van der Waals interactions between the ligand and the solvent are turned off. So essentially, the solvent is gone, or the ligand has disappeared from the solvent. Then you introduce harmonic restraints that move the ligand into the correct position, like essentially where it would be if the protein were there. And then you turn on the van der Waals interactions between the ligand and the protein. You turn on the Coulomb interactions, and then you remove the harmonic restraints. So these are the two physical endpoints, and these are the unphysical intermediates that connect them. Why are these unphysical intermediates needed? It's because all of these formulas that allow you to estimate free energy differences relies on something called a phase space overlap between the simulations of the intermediates. Okay, so essentially, every simulation that I perform in this chain shares some thermodynamic weight with its neighboring simulations. If you're unable to compute the ratios of thermodynamic weights between two neighbors in a simulation, you're going to have a bad estimate. Okay, so essentially every simulation will have some probability, will have some thermodynamic weight in the neighboring simulations. That's the most important thing. So that's the consequence. So that's the concept of phase space overlap. If your simulations have probability distributions that are very far apart, so if you look at the black curve with the red curve on the right, the phase space overlap is small, and then the error of your free energy estimate is going to be big. In OpenMM, there are a number of ways we have to optimize the phase space overlap between neighboring simulations. The Lennard Jones interaction is one of the most problematic ones. The reason for why Lennard Jones interactions are problematic is because the repulsion is r to the 12th. Now, if you have an r to the 12th repulsion, it really just looks like a hard wall. Okay, the hard wall looks, well, you might have the dispersion, and the hard wall looks something like this. Now the way to gradually turn off the dispersion interaction is the obvious way is just to scale it down by a constant. And as you turn off the Lennard Jones interaction, you're scaling this interaction down 90%, 80%, down to 10% until it's gone, right? But the problem is, if I scale the Lennard Jones interaction down by 50%, it still looks like a hard wall because it's r to the minus 12. If you try to plot r to the minus 12 and 0.12, they look the same. Okay, now even 0.1 times r to the minus 12 also looks like a hard wall. But the difference between 0.1 and 0 times r to the minus 12 is huge. And when you run a simulation, with no van der Waals interaction and a simulation with 10% of the van der Waals interaction, their thermodynamic weights are very different because you essentially have particles that are appearing like right on top of other particles, and that creates a very unhappy situation. And that's been a very persistent problem in free energy calculations, basically the turning off of the Lennard Jones interaction. Well, after that really long explanation, you might be getting some ideas that there are other ways to turn off the Lennard Jones interaction rather than just changing it with a constant prefactor. There are more intelligent ways to do it. So if you gradually turn off the Lennard Jones interaction by, say, while applying another formula that interpolates between the full Lennard Jones and the zero, maybe by using a softer repulsive core, you get a much better phase space overlap between your neighboring simulations and a much more accurate estimate. Okay. Here, this illustration just kind of shows that using a formula called thermodynamic integration, the free energy difference is just the area under the curve. And if you have these really huge slopes, you're not going to get a good estimate of the area under the curve. But if you have a smoother, if you have something that's smoother, you get a better estimate. Okay. There's also the issue of restraint potentials. Now, if you're doing a binding free energy simulation, one of the steps is to make the ligand disappear from the binding pocket of the protein. Right. Now, as you make the ligand disappear from the binding pocket, its interactions with the protein are going to get weaker and weaker. And when you get to, say, the 10%, like 10% of the ligand being in the binding pocket, it's going to start moving around because the interactions are so much weaker. And as this ligand starts to move around, it's going to sample your entire simulation box. And if it diffuses out, you might need to wait for it to diffuse back in again, and then you're back to the old problem of having to run a really, really long simulation, right? But you can see that the large-scale motions of this ligand that's only partially there have to do with its translational and rotational degrees of freedom, and you can remove those degrees of freedom with a harmonic restraint and add them back in analytically afterward. So that's basically the value of a harmonic restraint. It keeps your ligand in the binding pocket even when it's only 10% there, and that also helps to address this problem of sampling. So this here, this is a movie. I didn't make these movies, and I'm not even sure if they're playing. Hold on. The movie's not playing. That's too bad. Well, we'll have to. What you would have seen in the movie is that this molecule, which is the ligand, it's translucent, right? And the transparency tells you how much, like how strong the interactions currently are with the protein. If it was fully opaque, then that's the full interaction, and if it was completely transparent, then the ligand's not really there. And when the ligand becomes completely transparent, then it doesn't really have any interaction with the protein, and it's allowed to freely move around in the binding pocket. So I'm sorry that the movie didn't work, but we're going to move on. Okay. Once you've run these simulations, you have a whole lot of data, but you might have something like 50 different simulation trajectories, but at the end you want just one number, right? You want one number, you want the binding free energy or the solvation free energy. So how do we take all of this data and apply some equations to get the number that we want in the end? You use these statistical estimators of the free energy difference. So basically, there's always an equation that connects the estimate of your free energy difference to your simulation data. And they usually have to do with the ratio between two Boltzmann factors. Okay, that's why you ran simulations that have good phase space overlap. But not all estimators are created equal. Some equations are better than others. For example, you have thermodynamic integration. I actually kind of like this method, but you see, basically in thermodynamic integration, you are simulating the derivative of the free energy difference with respect to this, turning the interactions off and on. And depending on the number of points that you simulate And depending on how you do this numerical quadrature, that could bias your result or give you errors. There's also free energy perturbation, which is a very simple formula that's been around for a long time. The problem with that is that it involves taking straight averages of exponentials, and every time you have an average of an exponential, it should make you worried, because these numbers can vary over many orders of magnitude, and it can suffer from a really big bias. And there's also something called Bennett acceptance ratio, which is closely related to the weighted histogram analysis method, which performs better than free energy perturbation, giving you an estimate given the same data. Okay, and one of John Kodera's main contributions is to extend the idea of Bennett acceptance ratios to multiple simulations. So that's called multi-state Bennett acceptance ratio, or MBAR, and there's a Python implementation available also on simtk.org. That's kind of a recurring theme. You can find things, cool stuff on simtk.org. Okay, and this script has been around for a while. You can dig into it and look at the equations if you want. It's going to be a part of the exercise this afternoon, and you'll find that the analysis script itself is very standalone. You don't actually need to look at the equations in order to use it. And well, I guess that wraps up the presentation for now. It was only 15 minutes, but if you want to learn more about free energies, we do have a breakout session this afternoon where you can actually you can actually compute the hydration-free energy. We have an example that you can just run, where you can get the hydration-free energy of a single water molecule. I know that sounds really weird, but to make the exercise more interesting, you can modify that example to do a hydration-free energy of another molecule. We have it set up so that you can set up a simulation to get the hydration-free energy of ethanol, and you can even experiment with other molecules, and I think that's pretty cool. Okay, so with that, I'd like to thank you again.